Okay, so welcome everybody, and it's my pleasure today to introduce Professor William Duke, who is visiting EUB for this week, and he's being here with us in the unit of number theory at the Center for Advanced Mathematical Sciences. I'm just going to give a brief introduction to Professor Duke. Professor Duke finished his PhD at NYU under the supervision of Professor Peter Sarnak. And then he took positions at UC San Diego and then at Rutgers University. And he's currently a distinguished professor of mathematics at UCLA. Distinguished professor of mathematics at UCLA and the chairman of the Department of Mathematics there. Professor Duke has many honors and awards. I'll mention some of them. He has been an invited speaker for the International Congress of Mathematics in Berlin in 1998. He is a Clay Institute of Mathematics. He has scholarship. He has the Simon Fellowship, and he's a visiting professor also at ETH in Zurich. Besides, we are very happy to have him here with us to speak about the representation of integers using quadratic forms. So please join me in welcoming Professor Duke.
Well, it's a great pleasure for me to be here. It's actually quite an honor. I've heard about this university for many years. I've always been curious to come here. So I'm very glad to be invited. Now, let me say at the onset that my abstract for this talk, I made it sound like I was going to become quite advanced toward the end. But I was asked to give a more technical lecture on Wednesday. So I tried to make this lecture as accessible to non-mathematicians as possible. So we'll see if this is successful or not. So the title is Representation of Integers by Quadratic Forms. Now, this topic is one of the oldest topics in not only in number theory, but in mathematics. And it goes back to Pythagoras and Euclid and people of that era. So let me give you a brief outline of my talk. Oh, now it's not going to work. Okay. Now it works. Okay, so what is the subject of the talk? Well, so a basic task of number theory is to solve polynomial equations, typically, in several variables. And the thing that makes it an issue for number theory, as opposed to, say, just algebra, is that the polynomials have integer coefficients, and you look for integer solutions. Sounds very elementary, but it actually turns out to be extremely difficult to do this in some cases. So, well, linear equations we can handle, but after that, quadratic equations, and already things become quite difficult and interesting. Sometimes it's hard for people to believe this. So, with quadratic equations, it turns out the most interesting case are in 2 or 3 variables. There are reasons for that. I think the basic reason is because when you have more variables, you have a lot more freedom to find solutions. And 2 or 3 variables turns out to be kind of a critical case. One variable is not very interesting. And even with these simple examples here, x squared plus y squared equals m, and x squared plus y squared plus z squared equals m, there's an awful lot of interesting things to do with these 2 simple examples. I'm mostly going to talk about these examples. Okay, so what are the things you want to do with such an equation? Well, first of all, you want to know whether or not there are any integer solutions at all. And this can be a very difficult question, not in these cases, but in general, that can be a very difficult problem. And you also want to know if they exist, are there infinitely many? In the examples we're talking about, no, the forms are positive definite. So if you have solutions, you'll just have finitely many. But sometimes you'll have infinitely many for different examples. If you have finitely many, a natural question comes after you've decided whether or not they exist. Suppose they do exist, then you want to know how many solutions are there. And this is where things get quite interesting. So let's say you know what that is. You have a formula for the number. Then you can worry about how the solutions are distributed. And I'll give you some examples about that, what I mean by that. But those are the basic things you want to do when you're faced with an equation at time. So let's look at this first example. Clearly, this is an ancient example, right? I mean, x squared plus y squared. If m is a square, this is the Pythagorean equation. This is essentially the simplest example. So we want to know when the solutions exist. Well, so we want to know which integers can be represented as the sum of two squares. So a natural thing to do in these situations is to try to first look at primes. So let's just pretend like we know nothing and we're going to just experiment. This is one thing I love about number theory is it's kind of an experimental science in some sense. You're not doing experiments in a laboratory. You're doing experiments now these days on your computer or on a piece of paper and pencil. But it's a process of discovery through experimentation. At least that's how I look at it. Right? But the difference is, in physics or other sciences, when you come up with a hypothesis that you think is true, you kind of prove it, but the way you prove it is you compare it to what's already been established as being known. Whereas in mathematics, you actually have to prove it. So it's a different, how do I put it? It's a different standard than in other sciences. You actually have to have a logical proof. Well, you can argue, you're doing logic and you're reducing it to things that you think are known. Yeah, you reduce it to axioms. And this is a whole nother issue about, which axioms do you accept as being true? Okay, well, anyway, let's look at this example. So m is going to be a prime, and I don't know much. Well, 2 is the sum of two squares, 1 squared plus 1 squared. Try 3, and you won't find any. Now, the nice thing about this equation is you don't have to test infinitely many examples because x squared plus y squared is always positive. So you never have to go beyond square root of m to test and see if you've got it. So there's none for 3. Yeah, 5 has got 1 squared plus 2 squared. 7's got none, 11's got none. 13's got 1, 2 squared plus 3 squared, and also 17. Okay, so what's going on here? So, the other thing that happens here is it's going to turn out to be important that even though 5 is 1 squared plus 2 squared, you have all these different permutations and sign changes you can do. And that's actually going to show up in our analysis later. So there's actually 8 different ways, and we're going to distinguish between 1 squared plus 2 squared and 2 squared plus 1 squared. Seems kind of silly, but that's what shows up in the analysis. Okay, so after m is equal to 2, you have to do more of this, really, I think more examples to really discover this. But it seems to be that the ones that are sums of two squares have the property that when you subtract 1 from them, the answer is divisible by 4. Well, except for 2. That's it. The old joke in number theory is that 2 is the oddest prime of all. It's the only even one. So anyway, the ones where it works seem to have the property that when you subtract 1 from the prime, the answer is divisible by 4. So 5 minus 1 is 4. 13 minus 1 is 12. That's divisible by 4. And 17 minus 1 is 16. That's divisible by 4. So, and if you look at the other ones where it doesn't work, they seem to have the property that if you subtract 3 from them, you get something divisible by 4. So the language that people use is that in the first case, you'd say they're congruent to 1 mod 4. That means when you subtract 1, it's divisible by 4. And in the second case, they're congruent to 3 mod 4. This is an old notation. I think it's probably made famous by Gauss, but it's a very handy language that's used in number theory a lot. Okay, well, I'm going to tell you the answer about what's true for primes is that always works. So that's actually if and only a statement. So if you take a big prime and you want to know whether it's represented as the sum of two squares, what you do is you subtract 1 from it. If it's divisible by 4, yes. It doesn't tell you, how to find x and y. Just this theorem says it exists. And this is one of it's not Fermat's last theorem, but it's a famous result of Fermat. The other thing that you can do is we're talking about primes. So you can wonder, well, what about non-primes? Well, there's a very nice decomposition formula, which it's just a simple algebra formula. And it tells you that if you have one representation of an integer m1 as the sum of two squares and another one, then the product m1 times m2 definitely is the sum of two squares. And this is just simple algebra. You can multiply this out and check that this is true. So it tells you actually how to find the representation of the product as a sum of two squares. So just see, try it yourself and multiply them out. Of course, if you know about complex numbers, this is just the multiplication of two complex numbers. And by the way, that was one of the motivations behind their invention, was to handle this formula. And we also have a trivial result. So even though you don't have a prime, if you have a square, of course, it's the sum of two squares. We're allowing zero. Okay, so if you put together these three things, Fermat's theorem, which I haven't proven, but let's accept it as being true, and the decomposition formula and this trivial result. Well, okay, let's do an example. I wrote down lots of examples. So suppose we have 5 is the sum of two squares, and we have 9 is this trivial sum of two squares. Okay, 45 is the product of 5 times 9. And so you can use that formula to figure out which two squares 45 can be written as. So x1, x2 is going to be 1 times 0, y1 times y2 is going to be 2 times 3, and so on. x1, y2, 1 times 3, x2, y1, 2 times 0. And voila, you get 6 squared plus 3 squared, which is indeed 45. Okay, but you can put this all together and you can get a complete theorem about which integers can be represented as a sum of two squares. So what is it? Well, a positive integer is a sum of two squares if and only if, when you look at its prime decomposition, those bad primes congruent to 3 mod 4 need to occur to an even power. They're basically squares, right? Yeah, they're squares of something. And that's a complete answer to the first problem for this equation. And this is a very, very old result. Okay, so now we know which integers are sums of two squares. Again, taking for granted we have Fermat's theorem. So now we want to know, can we count the number of ways? And with 5, there were 8, if you count all the different combinations and sign changes. Well, again, I'm going to tell you the answer and then we'll play around with it a little bit. So let D1 of M be the number of divisors of M that are congruent to 1 mod 4. So these don't have to be primes. It could be any divisor, any integer that divides M. And similarly, D3 is the number of divisors that are congruent to 3 mod 4. And this famous result of Jacobi is that for all integers, we have this lovely formula for the number of representations of M as the sum of two squares. Well, it's in terms of these divisor functions. In some sense, it's more of an identity between two different kinds of arithmetic functions. But the divisor functions are actually quite a bit simpler than this function. So I think of this as a formula for our. Okay, where's this coming from? One thing about it is that it implies all the earlier results. It implies Fermat's theorem. It's stronger. Well, why is that? Because if M is congruent to 3 mod 4, let's compute what it says. So D1 of M is the number of integers congruent to 1 mod 4 that divide it. Well, the only one that works is 1. 1 always divides everything, and it's congruent to 1 mod 4. So that's okay. So that's this 1 right here. On the other hand, if M is a prime congruent to 3 mod 4, it's also going to contribute to this term, and I'll give you a 1. So the difference is 0. So that's Fermat's theorem in this case. Now, similarly, if M is prime congruent to 1 mod 4, we can play the same game. And now for D1, we have 2. We have 1 and M. And D3 is 0 because 1 doesn't enter in. So you get 2 times 0. And then you have this 4. This 4 is taking into account all the sign changes. So we have 8. Okay, great. So this is actually stronger because not only is it saying, for example, with 5, we had 8 solutions. This is saying any prime congruent to 1, 1, 4 will have 8 solutions. On the other hand, the decomposition formula also has a quantitative version. By that I mean it's a counting version. And this is what it says. Well, this 4, it's really, sometimes it's better to factor it out. So let's factor it out. Because from Jacobi's theorem, it's always divisible by 4. So let's call that R star then. Then this is a version of the decomposition formula. It's telling you you can get the number of representations of a product in terms of the numbers of each one separately. So it's about as simple as you can get. Now there is a proviso that they have to be relatively prime to each other. That means they don't share any prime factors. If that happens, it's a little more complicated. You could actually write down a formula for what happens in that case as well. But this is pretty satisfactory. So again, just as an example, we had 45 was 9 times 5. Let's just check out and make sure that this Jacobi theorem seems to be when you have a non-prime. So if you look at the divisors of 45, they're 1, 3, 5, 9, 15, and 45. Check that. So D1 of 45 is 4. Which ones are those? There's 1. These are the ones congruent to 1. So if I subtract 1 from 1, I get 0. 1 from 5, I get 4. 1 from 9, I get 8. And 1 from 45, I get 44. So that's 4 of them. And the other 2 are congruent to 3 mod 4. So what do I get? I get that there's going to be 8 solutions. And I actually wrote them all down because we got them from the decomposition formula. And Jacobi's theorem gives us 8 also. That was 4 minus 2 times 4. And also you can check out this decomposition formula. Okay. Now, I'm not going to actually prove Jacobi's theorem, but I'm going to give you one sort of sketch one approach that's very commonly used in number theory. One of the things that attracted me to this subject is that a lot of things that you can prove about integers, one of the most basic things, there's a famous saying that God created the integers and all else is the creation of man. And there's nothing more basic than the integers, right? I think most people would agree with that. It's hard to imagine anything more basic. Well, anyway, what attracted me to the subject is in mathematics, you have lots of sophisticated theories and tools, and especially in analysis. So it turns out that you can prove a lot of things in number theory using analysis. And that it's usually called analytic number theory. This is the thing I love. And this Jacobi theorem is a nice example. Now there's different proofs of this, so I'm not going to give you, all the proofs, but this is a technique that works in this case, which is very nice. Well, first of all, what have I written down here? So I've written all Q's, think of Q as a variable. I've raised it to all the square powers and added them up. Now, these dots mean there's infinitely many in both directions because there's infinitely many negative integers and positive. And what I'm going to do is I'm going to square that. Well, the reason is because when you square power series or you square polynomials, the result is that you add the exponent. I probably should have put this here. If you multiply q to 1 power times q to another power, you add the exponents, right? So that's how you get to sums of squares. So this is called a theta function, and I've written it. In this case, I've just taken the negative guys and the positive guys and put them together. And if you square this out, you actually do this. You can't give all the terms, but you can see what the pattern is. You get 1 plus 4q plus 4q squared plus 4q to the 4th. The integers you get up here are the ones that are summed of 2 squares, and the coefficients are the number of ways of writing it. It's really cool. So then, it basically encodes what's going on in a formula. So that's what you get here. Now, if you let R0 be 1, well, 0 is sort of the sum of two squares. It is, right? 0 squared plus 0 squared. Then you have what's called a generating function of this counting function into a function, it's a power series squared of q. Okay, so that's kind of like a nice way of expressing all the RMs at once. Now, you can try to look at the right-hand side of Jacobi's theorem, which was difference of 4 times the difference of divisor sum. I'm going to try to build that up just because most people are familiar with geometric series. So if I just take the sum of the powers of q, I have this very simple formula for q over 1 minus q. I'm not going to worry too much about convergence, but if the absolute value of q is less than 1, then this is a convergent series. Now I can certainly replace q by q to a power. That's still going to be less than 1. So I replace q by q to the n, and then I get this formula. I haven't done too much there. But now we're going to do something different. We're going to sum over this n that we introduced. And we'll collect together the terms where n times L is equal to another n for n. And if you do that, you get this divisor function coming out exactly. Because you're just seeing how many ways can I write m as a product of 2 positive integers. And so if I sum that, that's what I get. Well, you can't really write that down as a simple rational function because it's not. But it's not too complicated. But that's not what Jacobi's theorem had. It had divisors where you had a condition on the divisor modulo 4. So this kind of is demonstrating the kind of games that you can play. So if you restrict to progressions modulo 4, I can write the right-hand side of Jacobi's theorem, which was really bad, in terms of these geometric progressions. So I can write it this way. So what I've done here is I've encoded the progression into the power sphere. Okay, so, well, I can take that a little bit further. I claim it's actually that simple formula. So it's a little bit of algebra going from here to here. I think I did it. I mean, you can check this if you're interested. So if I take the difference here, just get a common denominator. Notice that 1 minus q to the 4n is difference is squares. So it's 1 plus q to the 2n times 1 minus q to the 2n. So I can take this quantity and express it this way and finally get down to what I'm claiming, which is q to the n. Q to the n over 1 plus q. Okay, so what I'm saying is that the Jacobi theorem, which is about how many ways can you represent the integer as a sum of 2 squares, can be encoded in this identity between power series, saying exactly that. It's really cool. I mean, if you just don't know anything and you just start multiplying this out, think of it as a big polynomial. You did the same thing here. You see that the coefficients match. Okay, now the idea is I'm not going to just say it's true. How would you prove something like this? Well, Jacobi actually did use this, and he used elliptic functions to prove this, which is a form of analysis. But there's another way to do it, which is a little bit nicer, I think, and it's called to use modular forms. And you have some experts in modular forms in the math department here. They will like this. Okay, so the idea is to replace q by a different variable. So we'll use a complex variable, which is in the upper half plane, meaning its imaginary part is positive. We'll write q as e to the pi I times z, where z has positive imaginary part. Well, if you have e to the pi I, think of if I just plug I in for z, what I would get is e to the minus pi. Right? So that's a number less than 1. So if I do this in general with this kind of complex variable, the absolute value of this, it's a complex number, will be less than 1. So that's what I'm saying here. What enters in are called modular forms and functions. So this theta function, which was one side of the identity, sum of q to the n squared, if I write it in terms of Z, I get this. Okay, now I haven't done much here. All I've done is just replace Q by e to the pi I times C. And similarly, if I do this with the right-hand side, I get this kind of series. Now, the point is that as functions of Z, these functions have some really interesting properties. They're a kind of periodic, right? Everybody knows about periodic functions, sine, cosine, and the like. Well, these are functions which are periodic, but in two variables. So well, first of all, they're holomorphic. This means that they have derivatives in the complex sense. So they're really nice functions. You could think of them as super polynomials. They behave like polynomials with infinitely many variables. And furthermore, the theta function doesn't have any zeros. Well, you just have to take that on faith. Now, what I'll do is I'll take the quotient of these two. Okay, now the quotient, theta squared has no zeros, theta has no zeros. This quotient will be holomorphic in the upper half. But the thing about it is it satisfies some what are called functional equations. So if I replace Z by -1/Z, now the effect of that, here's the upper half plane. The effect of that is that it inverts numbers in the unit circle. So it takes points inside the unit circle and flips them to the outside. If you're on the unit circle, it could move you. If you're right here at I, it leaves you alone. If you're over here, it flips you around over here. So it turns out that that function I wrote down is actually invariant for that transformation. Now that's not trivial to see that. Both of these are invariant. So both of these have a transformation rule which makes the quotient invariant. Now they're also clearly invariant under Z goes to Z plus 2. That's the other thing about this, because putting the Q, expressing it in terms of Z, makes it easy to see why this would be periodic in Z, because it's an exponential function. So it's cosine plus I sine. So it's periodic in the Z variable. So this quotient is invariant under these two transformations. Well, again, so Z goes to -1/Z flips in the circle. Z goes to Z plus 2 just shifts. So what the result is that function is completely determined by its values in this F, which is fundamental domain. So just like if you think of a periodic function, it's completely determined by its values on an interval. This function is completely determined by its values here. Now, the quotient also has pretty nice behavior in these, what are called in this cusp, where you head off. Now, it's hard to imagine, but this is really happening at infinity. And this is a hyperbolic geometry. So as we head into this cusp, you would never get there if you were traveling at a finite speed. It's very much like going up in this cusp. But the quotient has nice behavior in the cusps. So what you get is you get a holomorphic function which is bounded. And a bounded holomorphic function, it's not exactly Liouville's theorem, but it's very close to Liouville's theorem. So you can conclude that it's a constant. And you can figure out what constant it is by looking at the examples. So what you can conclude, and this is it's not a proof, but it's a sketch, is that this is equal to 1. Using analysis, right? Not using matching up coefficients, using analysis. So yeah, again, so I'm just recapping. So F is holomorphic and bounded. So we get that it's equal to a constant. That constant is 1. Well, so that's if you believe that, that's what gives you a proof of Jacobi's. Because Jacobi's theorem said this E is equal to that. Okay, so that gives you kind of a flavor for one use of a generating series. Now, there's a completely different kind of generating series that shows up here. And you've probably seen lectures on this. So let's recall the Riemann zeta function. Now, instead of having a power series, you have what's called a Dirichlet series. where the thing that's being raised to a power is just the integers. It's not a variable. So the variable occurs in the exponent. So this is the Riemann zeta function on the most famous functions in number theory. And the reason it's important is because it has a product formula, which is a product over the primes. And you can see this by using the geometric series again. And you can see that this was due to Euler. He realized that this formula is equivalent to the unique factorization of integers in prime. So it's another one of these things where you have a statement about integers, which translates into a statement about functions. So Riemann studied this function from the point of view of complex analysis, or acid of complex variables. And he proved that it actually has an analytic continuation. These series and product only converge for S because real part of S because of 1. But you can find a function which restricts to this series and product, but it's actually holomorphic in the whole plane, except it has a pole, it has a singularity in S1. If God had not made it have a singularity, we'd have no primes. We'd have no integers. We'd be living in a different universe. So it has many interesting analytic properties. So it has a functional equation, and the non-vanishing of it on the line real part of S1 leads to what's called the prime number theorem. And that's a counting function for the primes. So if you count the number of primes up to n, where n is a variable, you get this very nice asymptotic formula. So this is an approximation to the number of primes up to n. So this twiddle means asymptotic. It means that you take the ratio of the two, it tends to 1. N tends to infinity. The most famous unsolved problem, I guess, in mathematics, or certainly in number theory, is that the zeros of this function lie on the line, no part of S is equal to a half. And if that were true, everybody wants to prove this, but if that were true, we don't know how to prove it. Then it has a big effect on the distribution of primes, because the zeros affect this formula. This is like a first approximation, which only uses that there's no zeros to the right of 1 or on 1. Now, why am I talking about primes? We're talking about some of the squares. Well, it's actually closely related, because if you extend, the rational numbers, which is this Q, by joining the square root of -1, you get a field which is called the field of Gaussian numbers. So it's called the number field. And the reason it's interesting for us now is because it also has integers, things that are called Gaussian integers. So these are just where you let x and y be ordinary integers. So you can think of this thing as geometrically as being lattice points in the plane. And there's also Gaussian primes, which are irreducible. So in this case, you can think of them as just like ordinary primes. You can't factor them trivially into smaller factors, except for 1 themselves, -1 and I. Now we have I. Okay, well, there's a Riemann zeta function. It's called the Dedekind zeta function for the Gaussian integers. And you just basically sum up all the Gaussian integers, leave out 0, divide by this 4, which is the symmetry constant. And the reason it's interesting for me now is because this norm, it's called the norm, is just alpha times alpha conjugate. So it's x squared plus y squared, sum of 2 squared. It's showing up here. So another way to express Jacobi's theorem, a completely different way than the way I showed you before, is that this Dedekind zeta function for the Gaussian integers factors. So its coefficients are R of n, again because of this. The coefficients are R of n, and it factors this. It has a factor which is the Riemann zeta function, and another factor which is called the L function. So this L function, I have to define it. It looks like the Euler product of the zeta function, except you have this character. And what this is doing, I'm writing the sum of the divisor difference function in this form. And it's not completely obvious, but it's equivalent to this, where this character is 1 if p is 1 mod 4 and minus 1 if p is 3 mod 4. So it's just a different analytic way of expressing that formula. This L function has a lot of nice properties. It's very similar to the zeta function, except it has no form. Actually, entire. But it's a polynomial. So this is kind of a strange way of putting it, but Jacobi theorem implies that Gaussian integers actually have unique vectors. Why? Well, because we have this product formula. So this product formula actually implies that you have unique factorization in prime into Gaussian. So usually people wouldn't say it this way. So you also have a prime number theorem for the Gaussian number. So you can count the number of irreducible primes with norm less than n. And it's exactly the same. It's exactly the same. So the integer Gaussian primes are just the ordinary integers that are congruent to 3 mod 4. Their norm is the square. So they're like the trivial guys. But they're sitting there. So if you take them away, you still have the same asymptotic. Almost all of them are non-integer. Okay, now I mentioned that the third task of number theory is to understand more about the solutions. Now we have some clue about how many there are, and we know when they exist. How are they distributed? Well, so I plotted here the Gaussian primes up to n is 2500, where the norm is less than 2500. I actually computed these approximations. You can see it's not a great approximation, actually. It's kind of typical, actually. This approximation here is not that great. It's better, you could write down much better approximations if you don't use logarithms. I'll go into that. But the thing I want you to notice about this is how uniformly distributed they are. There's some cool patterns. Number theorists like to look at, that's what I mean by an experimental science. I will look at this and I'll say, what's going on here? Well, the first thing I'll notice is that they're very uniform. Now, one uniformity is just obvious, and that's the origin of the 4. There's a symmetry, right, between all 4 quadrants. So that's not surprising. But what are these squares here? Anyway, they're not all clumped together along one of the axes, for example. So you could ask, are they distributed around the circle? If you take a sector like this, would you find the expected number of them in a sector? And the expected number would be measured by the angle, right? You would expect there to be approximately 1/5 of them would be in here, if that's 1/5 of the way around. And so you can make that precise by saying you have uniform distribution of the arguments, the angles, would mean if you count the number in the sector with norm less than n, you divide by the total number, and that should be asymptotic to the angle divided by the total angle. So that would be called uniform distribution. So it only makes sense as limits because you're never going to have exactly the right number. Well, you could, but you wouldn't expect that to always be true. So it's a statement about what happens when n gets large. And this is a nice theorem of German mathematician Hecke, which he proved is true. So it's a refinement of the Jacobi theorem. It's telling you that you have prime, it's a refinement of the prime number theorem for Gaussian primes also. So it's telling you that you have the expected number showing up in a sector. And yeah, so what's behind this? Well, there's another famous mathematician, Hermann Weyl. He gave a very nice criterion for uniform distribution around a circle, which is what we have here. So he said, well, you don't have to look at any complicated function. You can just look at the exponential function and evaluate it at the angles you're interested in and sum them up, divide by the total number. Where m is an integer here. So if this tends to 0, every m, except for m equals 0. If m is 0, this is 1, and we're just going to get 1. But if m is not 0, you get lots of cancellation because this e to this power is a point on the circle, right? So if they're uniformly distributed, you expect them to be lots of cancellation. And you need to have enough cancellation for this to go to zero. If you know about Fourier analysis, the way this is proved is you take a characteristic function and you write down its Fourier series and look at each term separately, and that's what you have to have. And okay, so the theorem actually follows from looking at this more complicated zeta function, which is where you build the argument into the zeta function. So it's a highly non-trivial result. It's a refinement of the prime number theorem. Okay, so that was all the first example. Hopefully you've been convinced that that simple x squared plus y squared equals m is not so simple after all. That's what I love about math. I mean, the more you get into it, you realize you'll never you'll just scratch the surface. And if you're lucky, they'll let you see a little bit more. I mean, you're truly looking for something more, in my opinion. Okay, second example, sum of 3 squares. Now, here I'm just going to skip right away. So, to the analog of Fermat's. So, a prime, and I'm only going to talk about prime, is a very simple criterion for a prime to be a sum of 3 squares. It's if and only if it's not equivalent to 7 1. Okay, well, let's look at, there's no easy proofs of this. Another deep theorem. But you know, if m is a sum of 2 squares, it's obviously also a sum of 3 squares. Just by one of these. But let's look at the case where it's not a sum of 2 squares, but it is a sum of 3 squares. So for example, 3. 3 is not a sum of 2 squares, but it's a sum of 3 squares. Same for 11. Okay, so let's count the numbers. Call it R3 of it. This turned out to be really interesting. So when they exist, there's usually a lot of them. You know, when the Gaussian primes, when a Gaussian prime exists, there's only usually 2 solutions. Or there's 8 solutions, really, but there's only 2 really different ones. But this number actually grows in general. It gets pretty big, even for a prime number. And it's connected in very surprising ways with some other counting functions. It's connected with what's called the class number. So I'm just writing down an identity here. It doesn't really mean very much. But this q adjoint square root of minus m.
I don't know whose computer is this.
Okay, so now what is this? What's going on here? So this is an identity. It's also due to Gauss. And well, what's this h? So q adjoint square root of minus m is like the Gaussian integers when m was 1. But it turns out they're a lot more complicated. So the Gaussian integers have unique factorization into primes. But that's very atypical. If you adjoin the square root of an integer, negative or positive, actually, it's very atypical for you to put a negative integer. But the integers in this field to have unique factorization of primes. And this h is an integer which basically detects that. So if h is 1, you have unique factorization. If h is bigger than 1, you don't. It says more than that, but that's kind of the basic interpretation of it. So it's all 1 if and only if the quadratic integers have unique factorization. And so what I'm saying here is that this very basic counting function is connected to this very sophisticated function. And in fact, it's a famous theorem. It was only proved this last century. The famous result of Baker and Stark, that there's only finitely many m where the h is 1. It was called the class number 1 problem. And interestingly enough, the biggest m, prime m, where it happens is 163. Okay, now there's another old famous result which allows you to write the class number, hence R3 of m, as an analytic function. So this is this L function again. And now the character is related to M instead of -1. So this is called the Dirichlet L function again. And this N over M is the Legendre symbol. So what that means is if N is a square mod M, it's 1. If N is not a square modulo M, it's -1. If they have a prime in common, it's 0. So it's plus or minus ones and zeros. So it's a pretty sophisticated function. Now, it turns out you can sum this. This is an infinite sum, right? This is an infinite sum. N goes from 1 to infinity. Turns out you can sum this for these characters. And if M is congruent to 3 mod 4 and prime, there's a really simple formula for it. So this is kind of analogous to the Jacobi formula for the sum of 2 squares. But now we have this plus or minus going on, not just 1 plus and 1 minus. Now we have this more complicated plus or minus. And our sum is up all the way up to M, where M is this number here. So you can play around with this function as well. It's not even obvious an integer, because you have this M here. But it turns out, yeah, it's an integer. So here's an example with our 11. I just actually worked it out. So you have to go up through 10. And the squares modulo 11 are 1, 3, 4, 5, and 9. Well, 4 is obviously, and 9 are obviously squares. You can figure out which integer you have to square and reduce mod 11 to 3. Same with 5. And if you do this calculation, you add it up, you get 24. So that's the number of ways of writing 11 as the sum of 3 squares. Now again, you have lots of symmetries because you have sign changes and you have permutations that you can do. There's some subtlety because if you have 2 of them equal, permuting doesn't change it. So it's not completely trivial permutation issue. I did 163. This was fun. It's better to use a computer for this. But you can write down all the squares modulo 163, add up this formula, and then what's behind you is 24. Class number is 1, right? Our formula has 24 in it. And if you go back to the class number formula, there's a 24 in it also. Yeah. Okay, so I like to work out examples. So if you go back to this formula in terms of the L value, this can be proven in kind of a similar way that I sketched the proof of Jacobi's theorem using power series. And again, we can use power series, but now instead of squaring the theta function, we cube it. And the right-hand side is more complicated as well. So it's a little bit harder to do it this way. So I won't go into more details. Now, I mentioned that the size of this is pretty interesting. It's related to this class number. If you actually plot the size of it, so I divide it by 24, then you get this rather complicated looking picture. Now, if you look hard, you can see 163 here. That's the last time it ever was that low. But it seems to kind of staircase up. You can start to see kind of maybe patterns going on. So, well, what happens is there's always a lower bound for it. It can't get too small. And this is the famous result of Ziegel. It's called Ziegel's theorem. And it gives you a lower bound. As long as you have some representation in sum of 3 squares, there's a lower bound for how many you have. It's a very strange lower bound. Well, m to the half is not strange. This epsilon may not be strange. If it was, epsilon can be as small as you like. It could be 1 over 10 million. A very small number. But what the effect is the smaller that number epsilon is, the bigger the smaller this constant gets. So it's a statement. This has to be bigger than a constant times this. The weird thing about Ziegel's theorem is there's no way to figure out a constant given that epsilon. Oh, ineffective theorem. It's very interesting and strange theorem, but it does give you information. It says that this thing can't be too small. So I plotted more points. You can see, I actually don't know what's going on. I'm curious. I'm trying to figure this out. Why we're getting this kind of pattern. I have no idea. So I divided by square root of n. And actually, these can get small, but not very small because of this epsilon. Okay, now you might ask, what about uniform distribution? We talked about Hecke's theorem. What about the analog of this for 3 squares? Well, there's a big difference because there's apparently a lot of solutions to the equation x squared plus y squared plus z squared is equal to m if they exist. So instead of summing up over the prime, which we did in the prime number theorem and in Hecke theorem, we can take a fixed prime, but large, and look at those points. So now we're just going to look at those guys, which are actually, I think I forgot to say, no, so yeah, so these guys are also sums of 3 squares is equal to m. I actually forgot that. So x squared plus y squared plus z squared is equal. But I'm just taking the ones that lie in some set on the sphere and trying to count the number that are in that set and then divide by the total number. So this is the analog of what we did with Hecke. And you would say it's uniformly distributed. You could approach that. The measure of this set, well, the measure of this set divided by the total measure of the sphere. So the ordinary measure of the sphere. Okay, so here's a theorem that I was proved. I used the theorem of the advantage. When I wrote this up, this number scared me. 1988, my goodness. Been around a while. But anyway, this theorem says for a prime not equivalent to 7 mod 8, these points become uniformly distributed as m goes to infinity with prime. So this relied on a fairly deep result of Henry Riemann, and it's part of the whole general set of theorems. So now here's a picture. M is not very big here. M is equal to 251. So you always have this factor of 24, so there's not a lot of points. So I dug this one off the internet. That's a big M. I don't know how big it is. That's a big M. And you can see they're kind of, there's all these patterns going on, but they're uniformly distributed. They're not clumping around in some area. And similarly with the Hecke theorem, it comes down to a Weyl type criterion. But now you have to use the analog of the exponential for a sphere, which are called spherical harmonics. We have to use those guys instead of exponentials. And so you form the Weyl sum. And the original proof that I gave identified those with the Fourier coefficients of a cusp-form pathological equations, and that's what we apply this bound. So I'm not defining things here, so I'm sorry to wait. But I do want to mention that a few years later, in work with John Friedlander and Henrik, we gave a completely different proof, which is using subconvexity of L functions. This was an unknown term when we did this, and now it's a very relevant term. And it comes about by bounding L function. So actually, let me just skip through this. So the kind of L function you look at, an example is this famous cusp form of homogeneity. But we don't look at the cusp form itself. We look at the L function associated to it. So we take its coefficients and we make an L function. And then the problem becomes to bound it. So that subconvexity means you go beyond what's usually called the trivial bound. So at this point, it's getting a little bit hazy, but we were able to break the convexity bound. By the way, if you know the Riemann hypothesis, if you knew the Riemann hypothesis for everything, this would follow from that, actually. And we also need Ziegel's theorem because we need this 1/2. So we actually beat the 1/2 by a little fraction to get this theorem. Okay, so I'm definitely running out of time. So let me just mention that if you do 4 squares, there's a famous result that every integer is a sum of 4 squared. And that's a famous theorem of Lagrange. One other thing is if you start putting coefficients in, the whole game changes. So even with sum of 2 squared, if you put a little coefficient here, it becomes a much harder problem. a very beautiful book called Primes of the Form X squared plus y squared, all about this problem. And the other story is if you let the form be indefinite, and then if you have solutions, you have infinitely many. And then the distribution problems become extremely interesting. So you get questions about geodesics on the hyperbolic geodesics, how they're distributed. So I will stop.
Thank you. Any questions for our speaker? Any questions? Yes.
Yeah.
Good. Can you get closer? So, referring to Ziegel problem, so what prevents it from touching the square root of why we have this absolute?
Yeah, there's aspects of that picture I don't understand yet, but I mean, you can prove that there is variation. It's not strictly bounded by m to the half. It actually sometimes is below that for any constant. If you can prove that that can't be true. So it can't be exactly m to the half. Yeah.
Yes.
Understand the exact sense of the uniform distribution. For a nice set.
Yeah. Well, the thing is, you need to be able to approximate the characteristic function of the set by by some series of spherical harmonics. And you can make this set rather general. To me, I just put some conditions on having a boundary, and actually convexity. So I didn't want to mess with that aspect. But there could be interesting questions about that. So for me, I just let even a disk would be okay for me. So I wasn't that much interested in that question, but I think it's a good question. It becomes really a question of harmonic analysis, purely.
Convergence,
Yeah. Yeah, I guess I was getting a little sketchy there. But you project them down onto the sphere and you count the number that are in your set. Oh yeah, definitely. I didn't. There could be some weird pathologies if you look at sets like that. Yeah, I didn't try. It's a good question. I mean, the uniform distribution is a subtle subject. But those issues, I was just looking at sort of the basic problem. Yeah.
Yes. Yes.
What about them?
Cubes.
Oh, the cubes, sums of cubes, you mean? Oh yeah, then you're in much more complicated lands. I mean, typically you'll have only finitely many solutions, depending on what you're talking about, how many variables you have. When we have higher genus than zero, things become it's a completely different subject. But yeah, it's a natural problem. Yeah. I mean, the theory it becomes a problem in algebraic geometry and arithmetic geometry. So, for example, the theta function, the analytic side of things, really changes. It's not nearly as nice. So the quadratic case is very friendly to the analytic function approach, whereas the things when you have higher powers, the analytic side is not nearly as nice. Well, actually, the zeta function side is. It's very nice, but you have to look over finite fields. But the side that I showed doesn't really extend nicely. I tried many times over the years. Yeah. Things like the naive thing, like the functional equations no longer hold. that I use. I mean, the functions that you make do not have nice transformation properties in general. I'm not sure if I'm getting at what you're asking me, actually, but that's my understanding of what you're asking.
Any more questions? Yes, I have a question about the derivative function formula.
Yeah.
Where we have the sum of part of them, and equals the sum of squared.
Yes.
So I just want to know what's the motivation for the right-hand side, like we're breaking the values.
Well, it's an Eisenstein series. So it's a really great question. So, and I didn't go into that. So the theta function, the reason it has the transformation, so we're talking now about the generating function. The reason it has that is the Poisson summation formula. It's a formula from Fourier analysis, which tells you how to sum over integers of a function and its Fourier transform. But the function you're talking about is called an Eisenstein series. And the way it gets its transformation is by averaging over a group. It's a completely different origin of the functional equation. So it's another case where you have these two methods coming together. I didn't explain that at all, so it's a really good question.
I just want to know also, like, when we have the example about, okay, so you mentioned that squared plus n by squared.
Yes.
Equals, why would something like this approach work for this case?
It does. It does. Yes, it does.
Because I imagine like we can, like the n y squared, like twice greater.
It absolutely does. The complication is on the Eisenstein series side, you have to have a bunch of them. But yeah, it works and it leads to an incredibly beautiful theory. But yeah, it definitely works. You know, I'm happy with the quadratic case. I would love to do higher degree cases this way, but I don't know how.
Any more questions? Yes.
I did the cases. I didn't quite understand that. Well, what happens in four squares, every integer is the sum of four squares. So there's no congruence condition. But the congruence conditions do show up when you count the number. But I don't think it's quite as simple as you're hoping. It's a good question.
Yes, sir.
Indefinite. That's a great question too. So, at the end I was rushed, but if you have an indefinite quadratic form, then you typically will have infinitely many solutions. But there's something nice happens. You have groups of symmetries which map solutions onto themselves. So you can divide up the solutions into classes, and you can try to count classes of solutions. It's a really interesting thing. So, in this last picture, these are actually classes of forms. It's not a very great picture, but yeah, it's a very interesting question. You typically will have lots of solutions if you have an indefinite form. Yeah, this is an example. I mean, I haven't explained it, but this is the simplest ternary quadratic form. It's okay. Get this, it's b squared minus 4ac. Sound familiar? It's a discriminant form. That's a ternary quadratic form in A, B, and C, and it's indefinite. And this is looking at the solutions where the solutions are indefinite.
And if you're interested in this stuff more, we have a talk on Wednesday at 3 p.m. But it's more involved technically than the talk. And let's thank our speaker again. Thank you. Thank you. Thank you so much.